All right, so this is the LateCenozoic. Last class, we finished up with the major events in the early Cenozoic, which were primarily things like the Paleocene-Eocene thermal maximum and the evolution of whales and other things. So today we're going to be talking about the LateCenozoic. All right, and we'll talk more about what this image is here in a minute. So some notes about class. I just want to make this very clear. Exam 3 is your final exam. It is not cumulative. So all lectures from the beginning of the Triassic to the end of class are covered. That means that your homework 4 and your project are also covered on this exam. And what I mean by the project is something I'll talk about in just a second. Your project is due the last day of class. Any format is acceptable. If you turn it in on paper, it should be brought to class. If it's turned in online, it can be turned in on Canvas up till midnight. All right, the time and date of your final exam is in the syllabus. It is at the same time as lecture. Or same room, not same time, same room as lecture. All right, so your timeline, again, any major event we've talked about, you have the very specific list on Canvas. How do we know when this event happens? What do we see? Etc. So for an example, the Great Oxygenation Event, it happened in the Archean approximately 2.7-ish billion years ago. We see the first rise in oxygen. How do we know? Now remember, you are encouraged to be as creative as you'd like. You can make a PowerPoint, you can make a song. Hopefully you have started this already. Now, the purpose of this isn't to irritate you. I promise this project is to kind of help you piece together what changes had to happen for life to have evolved the way it has. For dinosaurs to have evolved, we must have had things leaving the water. For things to have left the water, we needed to have a lot of free oxygen. To have a lot of free oxygen, we would have had to have evolved algae, right? So essentially, the project is just to help you synthesize the order in which things happened. So, fair game for your third exam is the order of the events. I'm not going to ask you questions like, what is the iron catastrophe? I'm going to ask you questions like, put the iron catastrophe, the Great Oxygenation Event, and the evolution of dinosaurs in order from first to last. All right? So you don't need to study all the specifics of your timeline for your exam, but you should be able to tell me the basics of when things happened relative to others. So a general list. All right. So, the Quaternary period. We are only 2 million years from present. Holy moly. All right, this class flew by. What's going on? Well, hopefully you're noticing that there are glaciers everywhere, right? Glaciers are coming down and covering parts of the United States even, most of Europe, even parts of South America are covered in glaciers. So clearly, it's gotten a lot colder since the last time we've spoken, all right? Now, we'll talk about this a little bit later, and again, I don't need you to know these names. The Anthropocene is something we'll talk about a little bit later. That's why there's a star next to it. But the Quaternary covers a couple different pieces. The Pleistocene, the Holocene, which is where we are technically in right now, and the Anthropocene. The Anthropocene is the only one I'm going to ask that you remember by name, but I promise that you probably will by the end of this lecture anyway. All right, so we have periodic glaciations that cause corresponding drops in sea level. A drop in sea level is called a regression. I paused so you could fill in the word. All right. So when we have these drops in sea level, we can often expose what's called a land bridge. All right. So land actually connects Asia and North America. It connects Europe to the UK, Britain. How might this help with evolutionary patterns? Well, if we have things living on land, they can start to move to new land masses. Just like we learned about with the Isthmus of Panama last week, we can start to see animals and plants migrating through different pathways. All right, so these fluctuations were pretty severe. These glaciers sometimes reached 40 degrees latitude, which is incredibly low, right? 40 degrees latitude is, past New York. So that's pretty low. It's very cold on Earth right now. All right. So the Ice Age typically refers to the age of the Pleistocene, but these started a little bit earlier, and that's not a detail I need you to know. What I want you to know is in yellow. There have been multiple ice ages that have happened in the Cenozoic, and I want you to be very clear that the movie Ice Age is not scientific, not even a little bit. All right, so fluctuations are called glacials and interglacials. Glacial periods are during the actual glacier conditions, cooler conditions. They are marked by lots of glaciers and an increased albedo. That is going to come up again. You need to remember what albedo is. Now, albedo is the reflection of sunlight off a particular surface. Ice has a very high albedo, meaning it reflects almost everything. It doesn't absorb sunlight. All right. Interglacials are those times where we don't have a whole lot of glaciers. All right. So here is what we're looking at here. The yellow, which is the stuff on top, all right, that is the warmer period. The stuff that's on the bottom in blue, all right, that is the cooler period. So here we have the warmer periods up here. Sorry for the weird marking that showed up there. And then we have the cooler periods down here. So interglacial, glacial, interglacial, glacial. Hopefully you guys are picking up on that. All right. All right. So we make the boundaries of the names on the geologic time scale right now based on these ice ages. You don't need to know that, but that is where we're naming them, just so you have that information. All right. So cold adapted, meaning organisms that like living in the cold, were strongly selected for during cold periods. Hopefully that makes sense. But things that can survive in the cold will do better in cold weather. All right, so that's what we're going to see a selection of during this time. Organisms that like and can handle the cold. On land, we see a trend towards larger bodied mammals. Why? Larger organisms are usually able to hold on to heat a little bit better. So, in times of glacial periods, it's probably a lot easier to have a slightly larger body size, okay? So things like elephants and hippos, they can actually hold on to heat a little bit better. Bears can hold on to heat a little bit better, all right? That's why bears can go through hibernation and be fine for that and a couple other reasons, all right? So these groups of larger animals are called megafauna, which means large animal, very literally. All right, you don't need to memorize this list. I'm just going to show you the pictures. The mammoth. So the mammoth here, this mammoth is an incredibly famous fossil. This still has the meat attached to it, and this mammoth is quite a few years old. The reason that it's preserved this way is because it was preserved in ice. So essentially, this is an incredibly freezer-burned mammal. We have the mastodon. Mammoths and mastodon are two different types of animals. They are closely related, though. We have the Irish elk. This is a massive elk. Saber-toothed cats. Cave bears. These guys would dwarf your average bear. And the dire wolf. These are easily 2 or 3 times the size of your regular wolf. Most of these groups went extinct by the Pleistocene. Why? Well, we're not totally sure. Let's go through some hypotheses. What are some of the hypotheses that you have in your head? You might be thinking that we just said that throughout this time we go through glacial and interglacial periods. That would mean that if these organisms that really are able to thrive in cold weather are all of a sudden experiencing an interglacial period, maybe they're not doing so well. We'll take a look at that. So it got warmer closer to their extinction, just like you can see where that yellow arrow is at the top. Right at the boundary of the Holocene, it gets warmer. So possibly climate change. All right, let's look at another idea. Climate change may not be the whole story. Humans, who we haven't talked about yet, they're coming onto the scene, but we're going to spend 2 days on humans specifically. All right? So, humans may have played a hand in this. And we're not going to focus on them, just like I said, too much today, but we'll talk a little bit about this. All right, so as climate changed and as land bridges were exposed, humans dispersed into new areas. All right, so this is an image here from the McClung Museum of Natural History in Knoxville, Tennessee, that has a rich Native American history in that particular area. And this is where some of the areas in the U.S. where we see some forms of early hunting and butchering of megafauna. All right, so those large animals. So the overkill hypothesis. This is the idea that during the end of the Pleistocene, we had a rapid disappearance of megafauna, and that was caused by human hunting. All right, so take a look at this graph. Everywhere you see the arrow means Homo sapiens, human species, entered the area. And you can see that there's a drastic decline in large mammal population. So, were humans ruining things a long time ago? Well, that is quite possible. Let's take a look at this. All right, so again, there's a disappearance of many groups soon after modern humans first entered new areas. So some of the areas in question here are like Africa, Australia, North America, and Madagascar. Now, the overkill hypothesis is just a hypothesis at this point, meaning it's still being tested. We honestly don't have a whole lot of surefire evidence that humans were hunting megafauna. So if you imagine with me, how much effort do you think it takes to bring down a mammoth? And then to skin a mammoth, to cook a mammoth? That's going to take multiple groups of a large group of people, all right? But we don't know if we actually have that. We don't have a whole lot of evidence like cutting bone. We don't have that bone preserved. We don't have a whole lot of tools to suggest it. We see that it could have happened in a few isolated areas. We have evidence for that, but maybe not enough to bring down an entire group of organisms. All right? During this time, we don't have large hunter-gatherer populations. So we're not entirely sure if the human overkill hypothesis is explaining the trend we see. Maybe it's more likely a combination of climate change and human hunting. It could also just be climate change. I do want you to know a little bit about the overkill hypothesis, but you should also know that it's a hypothesis and there are some issues with it. All right, so here's the Pleistocene. This is called the last glacial maximum. Take a look at the amount of glaciers surrounding Antarctica and take a look at the North Pole. All right, it's pretty big. Now let's move to the Holocene. What do you notice? Hopefully you notice that from this picture to this picture, the glaciers have receded quite a bit, meaning they have melted, and that would cause a transgression. All right? So we see a general warming trend from the late Pleistocene into the Holocene. And again, these are just names of pieces of the time scale, okay? So this is going to bring us to an unusual event in Earth's history called the Younger Dryas event, okay? Don't worry about the older Dryas event. It's not very major, so we're only going to talk about the Younger Dryas event. This had an onset and let me rephrase, I'm sorry. It began and ended very abruptly, meaning very quickly, all right? And this time, I actually mean abrupt. I mean this happened over the scale of decades, all right? Please do not confuse this event with the PETM. These are two very different events. And this event gets its name from this beautiful flower right here called Dryas octopetala, all right? So, it is an indicator flower, and what that means is, anywhere you find it, we know it must be fairly cold. They mostly live in the Arctic, but if it's colder outside, they can spread further. All right? Now, Dryas has a very specific type of pollen, so we can see this very clearly in the fossil record. In the pollen record from the time of the Younger Dryas event, the record of the entire globe just about is filled with pollen from this flower that only likes cold air. What does that mean about global climate? Hopefully you're thinking that means that it was pretty darn cold outside. All right, great. All right, so we know it must have been pretty cold because this flower cannot survive in warm climates. And again, this is what the pollen record of Dryas looks like. These things are tiny and they're numerous, which means they can stay for quite some time. All right, they're pretty easy to find in the fossil record. So let's take a look at this graph right here, measuring isotopic evidence. We see the Younger Dryas event. It's highlighted right here. All right. What we see there is a giant drop. All right. It goes straight down. This is temperature in degrees. All right. Now, how are we measuring this, do you think? Hopefully you're thinking it was measured by oxygen isotopes. You would be absolutely correct. All right. So, shutting down thermohaline circulation. We talked about this last class with the PETM. How do we shut down thermohaline circulation? So we talked about it with the PETM and with the Permo-Triassic extinction. But during this time, if you heat up water enough, it can actually stop density differences between cold and warm water, and it can stop the flow of circulation. Well, if we can do that with warm water, do you think it's possible to do it with cold water? If we introduce tons and tons and tons of cold water, will the thermohaline circulation still be able to act like it usually does? The answer is probably not. So, thermohaline circulation can work if we either heat up the oceans or if we cool them down extremely fast. All right? So, the thermohaline, let me rephrase. What is the most likely explanation for the Younger Dryas event? Is we had a significant period of warming on Earth. That warming melted glaciers faster than expected into the water in the North Atlantic. It interrupted thermohaline circulation. All right, so the oceans got super cold because the Earth started warming up rapidly and it melted a ton of glacial ice, and it actually stopped thermohaline circulation for a little bit of time. It really kind of screwed up the ocean for a little bit. Now, volcanic eruptions and the Younger Dryas event. What do these two have to do with each other? Volcanic eruptions, we've talked about them a lot, and we've said that, they spew a lot of CO2 into the air, which of course warms the atmosphere. But remember, volcanoes can also cool down the environment. How are they doing that? Hopefully you were thinking that they are doing that by the presence of ash. All right, so many volcanoes give off more ash than others. The more ash that comes out, the easier it is to block out sunlight. If we block out sunlight, it's going to cool the Earth down. All right? So, for an example here, we have Mount Pinatubo. All right? This is a massive eruption in 1991. So, you don't need to memorize this. Just take a look at this real quick. I know there's a lot of ridiculous words on this graph. As the ash comes out, it's actually blocking out the sunlight. And you can see that through that gray cloud right about here. All right? We still have a whole... Oops, sorry, guys. We still have a whole ton of stuff going on up here. Lots of ozone destruction from all of this greenhouse gas that's coming out over here. But right here, we think it's actually getting cooler, even though it's warming it up. All right? So it cooled the Earth down by nearly 1 degree Fahrenheit for over a year, even though it destroyed part of the ozone layer. All right? So just remember, volcanoes can have a pretty strong effect on the atmosphere. So the take home. Huge amounts of ash may have taken longer to clear. The Younger Dryas event could have been caused by this very thing. All right? So, radiometric dating from carbon-14 is possible from the Pleistocene onward. Carbon dating only works for things under about 70,000 years old. How come? Hopefully you're thinking the half-life is too short. Yes, you learned that on your first test. All right? Now, what this means is we can actually start to see very small climate patterns throughout very modern rocks. From about 70,000, 100,000 years ago onward, we can see rocks that are incredibly well detailed. And what you're looking at here is the amount of carbon dioxide and methane that's present from many thousands of years ago. So 400,000, 50,000 years ago, we can see very specific trends. And what's kind of cool is I hope you notice here that all these graphs almost match up. They're measuring different things, and yet they almost match up. We see oxygen 18 here on this side. We see temperature on this side. We see the amount of CO2, amount of methane, amount of solar insolation here, and they all look like they're following the same pattern, don't they? All right, so I'm going to need you to write something down here because you're going to do your own in-class assignment for this, all right? Certain species of foraminifera, the things that make up those shells that we talked about a while back, we use them to figure out oxygen 18 dating. They will look different depending on water temperature. Forams, these specific species of foram that you're looking at right here, will coil to the left when the water is colder, and they will coil to the right when water is warmer. So what I want you to write down is left colder, right warmer. Left colder, right warmer. Okay? So what this means is if we find these forams in the fossil record, we can track changes in ocean temperature over time based on the direction that they're coiling in. All right? So here's our data. I'm not going to ask you to calculate it. I've already done it for you. We have the collection of how many years ago, the percentage of right and left coiling, all right, total numbers, etc. And we see here that we have the left coil. The left coil is this line right here. All right. And then the right coil here, this line right here. All right. So let's take a look at what is going on with the with our atmosphere from about present to 160,000 years ago. All right, pause the video. You are going to answer these 4 questions. All right, and I would suggest you work this out because you may see this on your exam. All right, so hopefully you have now unpaused the video. All right, hopefully you've answered these 4 questions. What does this tell us about ocean temperatures throughout the past 160,000 years? Are they stable? What does this graph suggest about ocean temperatures today? Warmer or cooler? How were the glacial and interglacial cycles identified on this graph? And finally, what would oxygen-18 isotopes look like from glacial and interglacial cycles? Meaning, what would be high oxygen-18 and what would be low oxygen-18? All right? Write down your answers. Make sure you understand this. All right, so case study. The Little Ice Age. So here is some old art history. All right, this was a couple of paintings by Henry Rayburn. Actually painted this a couple of times. This was actually painted in the height of summer. So for about 300 years or so, there was unusually cool temperatures. A couple different things were proposed: solar radiation, volcanism, ocean circulation, and this was 1550 to 1850. So this is really recent. Okay, we're finally at the time period where we have fancy people ice skating. So, quick question: why do we have seasons? Hopefully you are getting my hint here at the bottom of the slide that I will 100% ask you this on your exam. All right, this is a major science misconception. We'll get there in just a second. All right, why do we have seasons? I'll answer that in just a second. First, we're going to talk about Milankovitch cycles. Milankovitch was actually a prisoner of war, all right? So this is a really kind of a weird story, but Milankovitch was captured during a major war in Eastern Europe, and he was thrown into prison for a little while. And while he was there, instead of twiddling his thumbs, he decided to do some research. So he was doing some scientific data calculations. The prison was actually, they recognized who he was, so they allowed him to have some of those tools, all right, but not too much of it, all right, and he actually was able to do a whole bunch of calculations. And from prison, he actually found out that there are irregularities in the orbit and tilt of Earth concerning the sun. You do not need to know the times of the cycles, but there's about a 21,000, 24,000, and about a 41,000 year cycle, all right? So there are 3 cycles: eccentricity, we have obliquity, and we have precession. Okay? Obliquity is also called axial tilt. Please go to this website here at the bottom. You can access this through the PowerPoints and just click on it, or you can write this down here. This has a really good explanation of how all of this is working. Eccentricity. What you're seeing here is that Earth travels around the sun. We know that, all right? But sometimes it's more elliptical than circular, and it changes back and forth and back and forth, all right? And this takes a little while, but what this means is there are times on Earth where we are a teeny tiny bit closer to the sun than other times. Just a little bit, not a lot, all right? This can change the temperature on Earth by just a teeny tiny bit. Less than 0.3 degrees Celsius, I think, is about the max temperature change we'll see. Axial tilt. The Earth is tilted at about a 23.5 degree. We know this is tilted because a large planetesimal smacked into us many years ago, creating the moon. Hopefully you remember that, all right? So, sorry, I dropped something. Okay, so what this means is we have slight differences in solar radiation. If the Earth was standing straight up, the entire one side of Earth would be getting sunlight, while the other side of Earth would be in total darkness. It wouldn't be variable based on what latitude you were on, okay? It would be what side of Earth you were on facing the sun. This changes about every 41,000 years. And what this means is every 20,000 years or so, we have a switch between whether the northern hemisphere or the southern hemisphere has a slightly stronger summer or winter, all right? I think right now we're in the northern hemisphere having stronger summers. I'm not totally sure though. And then finally, precession. Earth's axis wobbles a little bit. It's like a spinning top, All right, so like a toy you'd play with as a kid, a spinning top, you could spin it and you would start to see it wobble just a little bit. Okay? What this means is what points north changes. Our North Star is not always our North Star. Our North Star right now is called Polaris. That isn't the case in the geologic record. We actually have different North Stars every 20 to 30,000 years or so. All right? So, why do we have seasons? Axial tilt. Axial tilt is the reason for all of the seasons. Pardon my terrible pun. All right? So, what this means is axial tilt or obliquity. We have more sunlight facing part of the Earth for every 3 months out of the year or so, every summer. For example, in Florida, Florida is pointing straight towards the sun, and that is why we have our summer. All right? And when we are in winter, it means we are facing the part that is not as close to the sun. Does that make sense? And that switches pretty regularly, and that is why we have seasons. All right. So, important question now. So if climate change can happen without humans, does that mean that climate change is completely because of the Milankovitch cycles? I want you to say no with me very loudly. All right? So the Milankovitch cycles. Every couple of years or so, a news anchor who's running their own show will say, I just learned about Milankovitch cycles. This is the reason climate is changing. It has nothing to do with greenhouse gases and human activity. That is absolutely not true. Temperature changes with Milankovitch cycles are not that big. It cannot and does not explain the climate change that we can see through data now. Anthropogenic, meaning human effects on climate change, are a cause for concern. The Milankovitch cycles really don't have a major difference or major change on Earth's overall temperature, and I want you to know that. So, what these squiggles are actually mapping out are the Milankovitch cycles, both axial tilt or obliquity, eccentricity, and precession are mapped out on these charts. How cool is that? We see this pattern reflected in all types of different data. All right, so here are your review questions. I hope you have enjoyed this lecture. I will see you next week.